Hi, my name is Max Itson, and this is my Lab 4 for Physics 2212. I apologize if my voice is a little hoarse right now, but I'm not feeling the best, and my voice is just gone. So, what are we going to be doing today? Well, today we're going to conduct a computational experiment to observe the behavior of resistors and capacitors. The purpose for this experiment is to apply our knowledge of circuits with resistors in series and in parallel that we learned in class, and to predict the behavior of ohmic resistors and capacitors. Here are a few physics principles we're going to be using today. The first one being Ohm's law, which says that the voltage is equal to the current times resistance. Capacitance will also be used today, as that is the charge is equal to capacitance times the voltage. And then a few principles that we're going to apply from class are going to be the loop rule, which just says that a round-trip potential difference for a static circuit is going to be 0, and the node rule, where the electron current entering a set piece of the current is got to be equal to the electron current exiting that piece of the current. Here's one of the starter circuits that we made. We used batteries, ammeters, and resistors. One of the questions that we wanted to answer was what would happen if we put the ammeter in backwards, and it just read a negative rating as opposed to the way it was set the first time. This is what happened when we replaced one of the ammeters with a voltmeter. We notice that the ammeter goes to 0, and that's because no current is flowing as the wires don't connect anymore. And the voltmeter disrupted the current and provides a potential difference from start to finish, which in this case is 3 volts. We then replaced the voltmeter with an ammeter so that the current may flow, and we calculated the potential difference at different sections of the circuit. We observed that there was a positive potential difference when traversing through the batteries and a negative when traversing through the resistors. The wires itself had no potential difference because they were merely carrying the current. By our loop rule, we knew that the net potential difference must be 0, so the potential difference caused by the batteries must equal the potential difference caused by the resistors in magnitude. To our expectations, we found that it was correct. We wanted to double check and calculate the resistance provided by different parts of the circuit. To our surprise, the resistors did not match up equally to the resistance we set them at. The wire and the ammeter resistance we found to be 0, because this is an ideal situation where the current flows through perfectly. If this were a real experiment, the potential difference may have been different, and thus a resistance would have been found. For our second experiment, we wanted to see how the light would react when we attach it to a circuit with a battery and a capacitor. We found that the light began to light up for 6 seconds as the electron current flowed through it, but once the capacitor met equilibrium, the light began to vanish. When we took the battery away, like we did here, it light up again and began to light up as the electron current flew the other way until the capacitor reached another equilibrium point. We then found that for the 10 ohm bulb, it took about 6 seconds until the light diminished, and it took 11 seconds for the 20 ohm bulb. In the next part, we calculated the potential difference across a capacitor at different points in time. We were aware of a relationship between the time constant and a natural log of voltage over initial voltage. So after plugging in data and observing the graph, we found a time constant of 5.99 seconds for our circuit. We also had some post-lab questions we wanted to answer. The first one was, what if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated one? And what's different about this real one and how it affected the circuits you hooked up to it? Well, if we use an actual one, the current would be lower because the ammeter itself would have a little resistance with it. Obviously, this is not ideal, so the online ammeter has the ideal resistance of 0, but that cannot be helped. It will be a source of error in our experiment. Our second question is, what if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Our ideal model would predict the capacitor to reach full charge instantaneously, as only a wire is connecting the battery with the capacitor and there's no resistance in the wire, so the electron current would be there instantaneously. However, if we did this in real life, it would not be instant, because they would both have a little resistance along with the wire connecting them, so the capacitor would reach full charge almost instantaneously, but not quite.